So now we will discuss module 2 topics. From this lecture onwards, we will discuss module 2 topics. Uh, I'll just give you an idea about what is module 2. In module 2, mainly we'll discuss the logic gates, okay, logic gates, and the mathematics the mathematics topics which used to control these gates, or instead of using the gate circuit level, we can perform the analysis on the mathematical way by using pen and paper. So that is known as the Boolean mathematics. And we will discuss different laws used in Boolean, that is De Morgan's principle of duality. And after that, we'll study different method that used to simplify or to represent the Boolean function. One of the method is known as SOP, and the other one is a POS. And we'll discuss one of the main simplification technique. It is known as a K-map. And finally, we'll discuss the Verilog language and how we can implement gates using Verilog language. In lecture 1 of module 2, we will discuss first we will discuss the NOT gate and its shape and the truth table and the logical operation. And finally, we will discuss the practical circuit which used to implement this NOT gate. Okay. And first, we will give an overview about what do you mean by NOT. It's also known as an inverter circuit. So either you can use this name inverter or a NOT gate, and it performs the operation called inversion. You can call it as a complementation. And the operation performed by the inverter is that it changes one logic level to opposite level. And in other words, we can say either it converts from 1 to 0 or 0 to 1. Means when you implement in a practical side, okay, we need to apply some voltage to represent then 1 and 0. For example, in order to represent 0 bit, I can use 0 volt. And in order to represent the 1 bit, I can use maybe 5 volt. Okay. On the practical side, to represent 0, I will use 0 volt, or to represent 1, I can use 5 volt. This is not compulsory. I can use any voltage to represent 0 and 1. For example, to represent 0, I can use 0 binary value. I can use a voltage level called 3 volt. And for representing 1, I can use maybe minus 5 volts. Okay. Any voltage we can use for a particular binary bit. But for the convenience, I will say that I will use 0 to represent 0 volt, and to represent 1 bit, I will use 5 volt. So there will be 2 levels. Okay. These are the 2 voltage levels. Either directly we can call it as, instead of calling this voltage, I can say this is low level and this is high level. Okay. To represent 0, I will use a low voltage, and to represent 1, I will use a high voltage. So this is one of the convention that we use. And that's why here it is indicated inverter changes one logic level to opposite logic level. Either we can see that it's low to high, or I can say from 0 to 5 volt, or 5 to 0, or I can say 1 to 0, or 0 to 1. Okay. So anyway, we can represent, or the function of the NOT gate is like that. It changes from one logic level to opposite logic level. And this is the symbol used in to represent the NOT gate. A triangle, and at the end you will put a bubble. Okay. And this is a symbol used to represent NOT gate, but in most of the circuit, digital circuit, when there is a bubble, it's actually indicating the NOT operation. So when you use very big circuit, instead of drawing like this, most of the time we will put a bubble to represent the NOT operation. So this also you should remember, whenever there's a bubble, it's actually indicating the NOT operation. Either you can use this NOT gate symbol, or in high, if the circuit is very big, usually we will use this bubble symbol to represent the NOT gate. And next we will discuss the term called a truth table. Okay. Truth table means which shows the output for the possible input. Okay. Means it gives the relationship between input and output, or it shows what are the different inputs. Okay, what are the different inputs provided, and what will be the corresponding output. This table is known as the truth table. So when you study any digital circuit, usually we will indicate the truth table of that particular circuit, and the truth table of the NOT gate is actually written here. Either you can use this convention like low high or high low. These letters you can use, or you can use the binary bits 0 1 0 1 etc. So in the case of NOT gate, if you are applying a low input at one end, at the output side you will get high. Okay, or in other words, you can say when you apply 0 at the input side, you will get 1 at the output side. And other input which is applied at the NOT gate is high. When you apply high at the output side, you will get low value. And similarly, in terms of binary, if you say if you apply 1 at the input side, you will get 0 at the output side. Okay, if you apply 1, you will get 0. If you apply 0, you will get 1. Or in other words, you can say if you apply low here, you will get a high, and if you apply high at the input side, you will get a low. So this information is known as the truth table. Okay, what are different inputs applied and what are the different outputs. Okay, and one more way we can represent the input output relationship, that is by using the timing diagram. Timing diagram means actually the graphical representation with respect to the time axis. Okay, uh, in the previous case we explained like the value will change from 0 to 1 or from low to high. Okay, instead of that I can draw the waveform. Okay, on the practical side, for example, if you are applying some voltage to the input of this particular gate, so assume that the time is 0, this is 1 second, that is 2 second, this is 3 second, etc. This is a time axis. Here I can indicate the voltage, and if you apply the voltage, for example 5 volt, for a duration of 1 second, and after for a 2 second duration I am applying 0 volt, and again after uh, 1 second I am applying 1 volt. So if you are applying a similar input waveform at the gate, what will be the output? So you need to draw the corresponding output waveform. Okay, what will be the output for the duration of 0 to 1 second, and what will be the output for the duration of 1 to 2 second, 3 seconds. So this information is actually known as the timing diagram. Okay, instead of writing zeros and one, we will draw the waveform, and the timing diagram is basically a graph that accurately displays the relationship of two or more waveform with respect to each other. So here you can see that we are applying a voltage T1 to T2, the value is high, and before that it is low, and after that it is low. And if you are applying a voltage like this to the input side, you can see that it's an inverter gate. So T1 to T2, initially it is high. Okay, during this duration is high. Now you can see it's low, and here it is low. Here you can see it's high. Here also it is high. Okay, so same information if you draw on a parallel graph, it will be like this. Okay, input at one side. Okay, this is the time axis. So this is the voltage. If you draw the two waveform on a single graph, it will be like this. So this is the input and this is the output. Okay, for exam point of view, it will be better if you draw both input and waveform on a single graph. Okay, then you can synchronize this waveform. For example, here you can see it changes from low to high. At the same time, output is changing from high to low. Okay, this information is actually known as a timing diagram, and this is one of the example to show the input-output relation of this NOT gate. And now we can do one question which is related to this waveform. If the input waveform shown in figure is applied at the input of an inverter, find its output waveform. So if you are applying this to an inverter circuit, what will be the output? So you can draw the corresponding waveform at the lower portion. Okay, so this is a time axis, this is a voltage. Assume that this is a voltage, and here this is A, and you can draw the output here, output waveform. So 1, this is 2, this is 3, 4, 5, 6, 7, etc. Okay, 0, 1, 2, 3, 4, 5, 6, 7. And see that from this point to 0, okay, from the reference point to 0, the input is 0. So during that time, you will get inverted output at the output side. You can use color. So this is output. From 0 to 1, here it is 1 voltage. So inverter output will be low. Okay. Again, from 1 to 2, the input voltage is 1. So we'll get 0 here. So if it is 1, here it is 0, here it is 0. And again, you can see that from 2 to 3, the input voltage is 0. So corresponding output will be high. Okay. And from 3 to 7, the input voltage is high. So your output voltage will be low. After that, you can see from 7 onwards, input is 0. So output will be high. So this is the corresponding voltage waveform of this particular wave. Okay. Now we'll discuss the Boolean algebra. Boolean algebra means actually indicating the mathematics of logic circuit. Okay, the max which we use to study the logic gates is known as a Boolean algebra. Okay, and instead of using the circuit, I can use variable and operators to describe the circuit. Okay, that's the advantage of Boolean algebra. We can use symbols plus, minus, multiplication symbols, or any dot symbol, or we can use different symbols and variables like a, b, c, 0, 1, etc. we can use to describe a circuit. Okay, that concept is known as Boolean algebra. And the Boolean algebra of NOT gate means we can represent this operation by using the variables. Assume that we are applying an input a and we are getting an output x, and you can write this operation like this: x is equal to a bar, a, and put a bar at the top. Or you can write a complement, this symbol also. When you refer the textbook, some textbook follow this pattern, but an exam point of view, or in a normal, when you are writing on a notebook, I prefer this particular method. Okay, a bar, and you can read like this: x is equal to not a, or x is equal to complement a. Okay, complement of a. In this way you can represent. So the output x is equal to a bar means, which indicates it's a not operation. Okay, x is the output, a is the input, and the output input output relationship you can represent like this: x is equal to complement of a. So now I'll explain the switching logic. Switching logic which used to represent the NOT gate. Okay, the circuit which used to represent the NOT gate, simply a switch. Okay, any gate we can represent by using a simple switch. A switch means either it can be in the closed position, okay, in the closed position, or in the open position. So this is the open position and this is the closed. Closed means there can be a current flow, and open means there is no current flow. So here we can expect an I, here we cannot expect an I because there is no current flow. And here you can see the voltage source is connected here, means there is a battery connected at this particular point. Okay, there is a bulb, and here you can see a switch which is indicated as A. And initial stage, assume that the switch is open. When the switch is open, the applied voltage or the current will flow in this direction. Current will not flow through the switch because the switch is open. So current will flow through this lamp and it will complete the cycle. So when the current flow through the lamp, so it will produce some output. Okay, or we can say the lamp will be on. This is one condition. And another condition, we can say that when the switch is closed. Okay, when the switch is closed, we can see that there are two parallel paths. Okay, one is like this, another one at the resistor. And if we apply voltage here, okay, this current will flow in this direction because this is a low resistance path or short circuit path, and this is a resistive path. So current will always choose the easiest path. So there will not be any current flow through this lamp path. So it will take the short circuit path and it will complete the cycle. Okay. So during that time there is no current flow through the lamp, so lamp will be in off condition. So when the switch is closed, the entire current will flow through this direction, and there is no current flow through this lamp, and the lamp will be in the off condition. So I can represent this condition like this. Okay. Uh, for the switch, there are two conditions. One is open, and another one is a close. And the lamp position. Okay. Again, two condition. One is on, another one condition is off. Okay. So you can mark like this. When the switch is open, the lamp condition is on. When the switch condition is closed, the lamp condition is off. So we got a table like this. Okay. And if you are saying open is equal to 0, and okay, if open is equal to 0 and closed is equal to 1, by using a symbol or binary bit I can represent. And here also I can represent on by using 1 and off by using 0. So you can see that is equivalent to the NOT gate truth table. Okay. If it is 0, the output will be 1. If the input is 1, output will be 0. So in this way we can achieve this particular NOT gate circuit. So instead of this switch, you can use a transistor or any other switching circuit you can use. Okay, this is the basic idea about what about NOT gate. Now I will explain what do you mean by the integrated circuit or the ICs available for the NOT gate. So if you take any circuit, this is actually the symbol of NOT gate, but the actual circuit will be entirely different. So when you search in the circuit, you can see some black box like this. So this is known as the integrated circuit IC. So NOT gates are available in this form. Okay, just like ICs. This is not NOT gate, but in the similar way, you can see the NOT gate also. So there are some standard ICs are available, and when you buy any IC, it will not write like NOT gate. So it will indicated by some numbers. Each IC is represented by some numbers. Okay, if you refer any IC, there will be some numbers. There is no wordings like NOT gate or something like that. So by using the symbol, by using the number, we need to identify which gate operation is performed by that particular IC. Okay. So next we will discuss the practical IC which used for NOT operation. And there are mainly two main technology that we used to manufacture IC. One is known as the CMOS and another one is TTL. For the time being, I will just give the name only. In CMOS means I can manufacture ICs by using the MOS transistors. Okay. MOS transistor or CMOS transistor. Another one by using the BJT. Mainly the component is BJT, bipolar junction transistor. Here we are using the FET transistor. Here we are using the bipolar junction transistor. If bipolar junction transistor is the main component of designing this IC, then it is known as the TTL series. And if the CMOS IC, the CMOS transistor is the main component, then it is known as CMOS series. So when you see a practical IC, it will be something like this. Okay. And most of the gate ICs are 14-pin ICs. Okay. When you use ICs in the lab and for the project purpose, mainly the digital gates are available in 14-pin IC, and different versions are available. This is dual inline package type IC, and there will be here you can see the dimensions to only to realize what will be the size of that particular IC. Okay, and when you take IC, the internal diagram will be you can see only a black portion at the top. Okay, but internally the circuit is arranged like this. For a NOT gate, it will be like this. And the standard name used for this NOT gate is here you can see 04, but there will be some prefix, and this prefix is normally 74 or 54. And this 74 is actually indicating the IC is a general purpose one, or a commercial or a laboratory purpose one. And if the series is 54, it is actually indicating it's a military purpose or industry application. we cannot use the normal general purpose ICs industry, because most of the industry is operating in a high temperature environment. So we need to develop ICs which withstand in high temperature also. So same function, but its characteristics are different. Okay, temperature withstanding properties are different. That's why there are different versions are available, 7.4 and 5.4 series. That's the most commonly used one, and both CMOS and TTL versions are available. But now we will discuss the standard one, 7404. So the IC number will be like this, 7404. Okay, and the 7404 means is actually a NOT gate. So when you going to purchase an NOT gate, they will ask the number. Okay, then you should say that you need a 7404 IC, and this is the structure of 7404 IC. And here you can see that a single IC contain 6 inverters. Okay, maybe you require only one, but you cannot use as a single one. You need to buy a single IC, but it actually contains 6 inverters. If you require only one, you can use one portion. You cannot cut, but you can connect input here and you can take output from here. So that's a symbol actually represent. Here you can use a second NOT gate by applying input at the 3 and output 4. And similarly input at 5, output 6. And the pin number 7 and VCC is actually used to connect the power supply of this particular IC. In order to work this particular IC, we need to supply some battery voltage, and here we need to apply the ground terminal, and here we need to apply the positive voltage. And in the upper side, here you can see here the lower side there are 7, and upper side also 7. So the numbering will be like this. You cannot change the numbering pattern. After this 7, here you can see 8 starts, 8, 9, 10, 11, 12, 13, 14. Okay, and the top side you can see that here ICs are gates are arranged like this: 9 input, 8 output, 11 input, 10 output, 13 input, 12 output. Okay, so this is the basic structure of 7404 NOT gate IC.